So my name is Siddharth Suresh. I'm a software engineer at SEF, and today I'll be speaking about metering and fees, a structure designed for fairness and efficiency. So why is a new fee model required? Currently in Stellar, we charge a fixed fee per operation, and this worked well until now because each operation is limited. And anytime we added a new operation, we made sure the upper bound of the runtime what made sense for the fee that was being charged, and the variance between the lower bound of the runtime and the upper bound was limited. But this will not work well for Soroban because the resources used by an invocation can vary greatly. For example, a Stellar Asset Contract token transfer, which doesn't instantiate a WASM VM, it uses a native contract, will be pretty cheap and won't use a lot of resources. But a complex liquidity pool swap could instantiate multiple WASM VMs in addition to having more complex logic. And this would end up using a lot more CPU. Or you could upload a large WASM contract, and that would end up using a lot more I/O. So this leads to my point that ledger capacity is limited, and it's limited by specific resources that I alluded to with the examples before. The first one is CPU. We have a limited amount of time to apply the transactions to the ledger. We have to close the ledger roughly every 5 seconds, so realistically, we have 1, maybe 2 seconds to apply the transactions. The next one is I/O. We can only read and write so much data per ledger. And the last one is transaction size or bandwidth. We can only flood so much data through the overlay before DOSing it. And it's important to note that the limits above need to be respected when the transaction set is built, so before the transactions are applied. So that the transactions need to be grouped based on the capacity available, potentially resulting in the exclusion of transactions from the ledger. So the resources I just mentioned make up one component of the fee, which is the non-refundable resource fee, but there are 2 more components. The second one is the refundable resource fee for work that's not restricted by ledger capacity. You look confused. No. Oh, okay, sorry. So the first one are the size of the events emitted, and the second one are rent bumps. And the reason these are not restricted by ledger capacity is that events are not stored on ledger. They're emitted in the transaction meta, and rent bumps are just a charge for extending the lifetime of your Soroban entries. So what does it mean for the resource, for the fee to be refundable? This means that you'll end up being charged for exactly what you use. So for example, say I set the refundable resource fee to 10,000 stroops, and after my contract runs, I only needed 8,000. 2,000 stroops will be given back to me at the end of the transaction. Now, you may ask, why does the first component not work like that? Why is it non-refundable? Based on what I mentioned in the last slide, we have to create the transaction set and we have to respect the limits from the transaction set before they're applied. So if I submit a transaction and I want to use, say, 40% of the CPU capacity on a given ledger, the network will allocate those resources for me, and I will pay for it. It's up to me to use those resources. So if I only end up using 5%, it doesn't matter. The network allocated 40% for me, and I will have to pay for it. And then the last component is the inclusion fee, which is the social part of the fee used for transaction prioritization. So let's talk a little bit about the transaction inclusion fee. This is required because there are limited ledger resources, and the protocol needs to be able to prioritize which transactions to include and exclude in the ledger. The inclusion fee is chosen by the submitter based on what they think the transaction is worth. So it's a bid for to get your transaction into the network, into the ledger. And we use a flat fee here, and a couple alternatives that we considered were using a single multiplier on the non-refundable resource fee. So you just say, I want to bid 2x of my non-refundable resource fee, but the issue here is that imagine that there's a lot of contention on CPU, but not I/O. If you use a single multiplier, you'd end up, the network would end up overcharging for every component in that fee. So instead, another alternative would have been to use a multiplier per dimension, per component. So you have a multiplier for CPU, a multiplier for I/O, and a multiplier for transaction size or bandwidth. But this becomes harder to use. Now, a user will need to keep track of all 3 markets when they want to determine what the bid needs to be to get the transaction into the ledger. An important detail here is that a discount can be given if no transactions were excluded. So in this case, everyone would just pay the base fee, which is 100 stroops. But if a transaction were excluded, then you'd be in the state what we call surge pricing, and you would end up paying the lowest inclusion fee across the transactions in the transaction set. So this is done for fairness. It's not fair to penalize a transaction for setting a higher inclusion fee when a lower inclusion fee would suffice. So I want to talk a bit about the right fee, which is the...
Sorry, just a really good question on inclusion fees. Are those refundable?
No.
No, okay.
Yeah. I'll move on to the right fee, which is a little bit special. And this is part of the IO component of the non-refundable resource fee. So to bound the growth of the ledger, the right fee depends on the size of the ledger, and more specifically, the size of the bucket list. So the bigger the size of the ledger, the more expensive it will be to write, as you can see in this graph right here. And in addition to that, there's this target size, and once the target size is hit, the right fee will grow much faster because we apply a multiplier to it. And this target size is a setting in the validators that can be updated through a validator vote. And the reason we have this is for the network to be able to determine an upper bound for it to stay healthy on the size of the ledger. And if it gets hit, it gives the network time to react to it instead of just allowing unbounded ledger growth. And while this is one mechanism that we use to bound ledger growth, state expiration is another area that Gerend will expand on in his talk right after this. So this talk is called Metering and Fees, and I've only spoken about fees so far, but metering is an important component here. So the metering system is used to track CPU and memory usage. And it's important to note that while we do charge for CPU, we don't charge for memory. We just enforce a memory limit per invocation. And this is done because memory is a use or lose it resource, and after a transaction is just given back to the system. And we don't expect contention on memory even when we move to parallel transactions in the future. And the interesting thing about metering is that we use a linear model instead of measuring actual cycles spent, because the validators use different hardware and the results will be non-deterministic, which doesn't work for consensus. And we use a set of components for these linear models. So an example of a component would be SHA-256 or IN256 multiplication or VM instantiation. Each one is a different linear model. And this allows us to update the settings for these models, which allow for fine-tuning. And that leads to my next point, which is that there's a lot of calibration that can be done between metering and fees. So the settings for both fees and metering are highly configurable, allowing the network to calibrate settings over time without a protocol upgrade. But the use cases for calibrating fees and calibrating metering are a little different. So for metering, the use case is mainly for making metering more accurate as we make the implementation more efficient, which reduces costs. So for example, say we optimize the VM instantiation code, and when we run the benchmark on a local machine, we see that the actual CPU spent dropped by, say, 30%. What we would do is deploy the optimization, and then through a validator vote, we would update the linear model, and this would reduce costs for the user. Now, calibrating fees are a little different, and this is mainly for updating fees based on network usage. So for example, if the ledger is always at capacity for transaction size, but not I/O, we could increase transaction size costs and decrease I/O costs. And this is, like in this specific example, this allows the network to distribute resources more evenly based off of what's available. And you can imagine a contract writer taking advantage of this by reducing the size of what it takes through a function parameter, and instead storing that information on ledger, right? And this is an example of making the transaction smaller, but increasing your I/O costs. So an interesting question to ask is how are existing Stellar operations impacted? While Stellar operations and Soroban operations are executed in separate phases, they run on the same validator and share the same ledger, so they share resources. So initially, the Soroban transaction limit will be set low enough to not affect existing Stellar transactions, but we may need to reduce Stellar capacity in the future to scale up Soroban. So finally, I'll talk a bit about best practices on setting your resources. So the most important one is simulating your transactions with Soroban RPC. And so RPC, in addition to setting your footprint, which are the ledger keys that your contract will touch, it'll also set the fees to an amount that the network should accept. And it'll even add a small cushion by increasing all the resources. But there's an important caveat to be aware of when you simulate your transactions, and it's that if the ledger state changes, the transaction submission can diverge from simulation, leading to a result you may not have expected. There's not a lot you can do here, but depending on the way your transaction is set up, there might be an alternative, which is that if the resources for a specific invocation don't vary much, so let's take a Stellar Asset Contract balance check, which just touches the Stellar Asset Contract instance and an entry for the balance. It's pretty simple. You can build the footprint for that, and then you could also compute the fees just by running simulating once, and you can just store these values. And then the next time you call this transaction, this indication, you could just use the stored values, which will let you avoid the round trip of simulating transactions with Soroban RPC. Now, this is a thing you can play with. It may not work for the transactions you're using, and it might make sense to maybe rerun the simulation once a day or once a week or once a month, just to make sure that if we make an optimization to say some component for metering, that you would end up picking up those changes and reducing your costs. Because if you remember, we don't refund for the CPU IO or transaction size. So if you overestimate for some reason, you're going to end up paying those amounts. And the next one is to make sure to add a high cushion to the refundable fee. Right? Any unused amount will be refunded. So if you remember, the refundable fee takes into account events and rent bumps. If you, for some reason, are trying to estimate exactly, the exact refundable fee you're going to use, this might be difficult because rent bumps take into account the current ledger number and the ledger number and the expiration ledger of the entry that you're bumping. So it may not be easy to calculate exactly when a rent bump will happen. And it would be very unfortunate if your transaction failed due to a low refundable fee, because you would still end up paying the fee for the failed transaction. So you should set this to an amount you're comfortable paying, like a reasonable amount, with the understanding that anything unused will be given back to you. And you should use fee stats to determine a reasonable inclusion fee. So take a look at Stellar Dashboard to see what the more recent inclusion fees were, and just to determine what you would need to bid to get your transaction into the ledger. And this is similar to how people use Stellar today. And finally, please optimize your contracts to reduce fees for the users. So don't make unnecessary cross-contract calls, because VM instantiations are expensive. Make sure your storage is set up in a way that makes sense for the access patterns of your contract to reduce IO costs for the user. And you should even optimize your WASM bytecode down. And you can do this by using the Soroban CLI. I believe the command is Soroban contract optimize, and this will strip the WASM bytecode down to the minimum required, which will reduce the the bandwidth costs when you upload a contract and the IO costs when you load the contract. And yeah, thank you. Thank you for listening. Yeah. Anything else? Yeah.